recording. Uh, Thank you, everyone. Sorry for this delay, but it's a pleasure for us to introduce Professor Charles Epstein for Center for Computational Mathematics at Firestone Institute. Professor Charles is a well-known mathematician, analyst, and work in PDEs. And today will be a very great pleasure to us to be held here in this talk. Professor, you can start. Thank you very much.
Okay, well, thank you. Thank you very much for the invitation, and I'm very sorry for the delay. Um, so I'm going to talk about some work I did recently on superconductors. Let me just see if I can get this to change page. Hmm. All right. That didn't work. One sec. Uh, no, why isn't it working? Okay, there we go.
Yes.
Okay, so this is work I've done recently, mostly with Manas Rach and Yu Guan, with a little contribution from Leslie Greengard, and Manas and Yu Guan did the numerical work. Um, so again, I like this quotation from Maxwell from his treatise on electricity and magnetism, where he says, "In the application of mathematics to the calculation of electrical quantities, I shall endeavor in the first place to induce the most general conclusions from the data at our disposal, in the next place to apply the results to the simplest cases that can be chosen. I shall avoid, as much as I can, those questions which, though they have elicited the skill of mathematicians, have not enlarged our knowledge of science." So I hold with this. Okay, so I'm going to talk a little bit about Maxwell's equations. I, when I use Maxwell's equations, when I talk about Maxwell's equations, can you see the pointer? Yes, okay. I write them in terms of a one form for the electric field, C, and a two form, eta, for the magnetic field. And similarly to solving Maxwell's equations is solving the Helmholtz equation. And in fact, the Helmholtz equation, the Maxwell equations with omega, mu, and epsilon all constants implies that the components satisfy the Helmholtz equation. So they're closely related. Okay, so we assume here that epsilon and mu are piecewise constant, and this is so we can use some sort of potential theoretic representation, a layer potential representation, to write down solutions. Okay, so the typical problem for the Helmholtz equation, for example, is in the Dirichlet problem in the exterior of a domain D. So D for us will always be a bounded domain in R3, and omega will be its complement. And the exterior problem is we try to solve the PDE in this exterior region, and we specify the boundary data. Now, because we're solving an equation for a frequency within the spectrum of the operator, you have to specify data to get a unique solution. So we specify that the solution should be outgoing. So in this case, we take the radial derivative minus IKU should be vanishing like 1 over r squared. Now, there's several ways you can write down solutions to this PDE using the fundamental solution, which has got this nice simple formula in 3 dimensions. We'll let gamma be the boundary of omega, so we can write it either as a single layer, just integrating over the boundary with the fundamental solution, or we take the normal derivative in the incoming variable, in the y variable, and we write it as a double layer. And either formula will define solutions to the equation in the complement of gamma. Now, it turns out that for static type 1 superconductors, we also have a representation that looks like Maxwell's equations. So what is a superconductor? Well, first of all, what is an ohmic conductor? A normal conductor. A normal conductor is a material in which the current, the flow of electrons, is related to the electric field by the simple formula that the current is a constant times the electric field, where the constant sigma is called the conductivity. Now, the first thing to know is that a superconductor is not an ohmic device with infinite conductivity. That is, it's not what would be called a perfect electrical conductor. And if you think about it this way, you'll just get into trouble. It leads to paradoxes. So within a superconducting material, there's actually a different constitutive relationship between the current and the magnetic field, which is called the London equations. And today, I'm only going to talk about static fields. So static currents, static magnetic fields, no time dependence. Because as soon as you have time dependence in a superconductor, the mathematical model becomes extremely complicated, and it's very difficult to analyze or talk about. Okay, so we suppose that we have a superconductor and it's contained in our region D, and within this region, we have the following constitutive relation, which is that D star eta, the divergence of the magnetic field is the current, which is standard. But D of the current is -1 over lambda squared times the magnetic field. So this is sort of the new equation. The fact that the gradient of the current, in effect, is -1 over lambda squared times the magnetic field. So it's a relationship just between the magnetic field and the current. And what we see here is that for a static current within a superconductor, you don't need an electric field at all. And of course, in a superconductor, as soon as you have electric fields, you run into this problem that they want to generate an infinite current. So it's a good thing that we don't have an electric field. Okay, now there's this parameter, lambda L, which is called the London length, and the current and the magnetic field are mainly supported in a neighborhood of the boundary whose thickness is a few multiples of this length. And essentially, equation 1 is essentially Maxwell's equations with wave number I over lambda L. Okay, so these are phenomenological equations. They were derived in 1935 by Fritz and Heinz London. They are proved to be quite accurate in many circumstances, and for many materials, they give very good agreement with the BCS theory, the Bardeen-Cooper-Schrieffer theory of superconductors, which dates from 1957, so actually many years later. And they agree very well with experimental results. So in particular, they predict what's called the Meissner effect, which is that a superconductor expels magnetic fields. Well, it doesn't actually expel them completely, but what happens is they decay very rapidly in the material away from the boundary. Type 1 superconductors have the following phase diagram, where there is an axis for temperature, the strength of the ambient magnetic field, and the current density within the superconductor. And this blue region sort of indicates the boundary of the superconducting zone, which is close to the origin of the coordinates. You like 0 temperature, 0 magnetic field, and 0 current to have a superconductor. Okay. The standard scattering theory problem for a superconductor, you have to specify both the boundary data and the boundary conditions. And in the current context, what we can imagine is that you have an incoming static magnetic field. So this is a field that's generated outside the conductor by currents in the complementary region. And as usual, the field in the exterior, omega, it's split into this incoming field and an outgoing scattered field. The total field we denote by eta plus. So it's the incoming field plus the scattered field. And the scattered field is outgoing, and that means it decays like 1 over the distance to infinity. And it satisfies these equations for static magnetic fields. So it's a harmonic 2-form. Now, there are no current sheets on the boundary of a superconductor, which is another thing that really distinguishes them from perfect electrical conductors. The current actually resides in a neighborhood of the boundary, but in a macroscopic sized sheet. So that means that the physically reasonable boundary conditions are that all the components of the magnetic field are continuous across the boundary. So if we let eta minus denote the magnetic field inside the superconductor, then eta minus minus eta plus restricted to the boundary, which would normally be called the normal component of the magnetic field, is equal to the incoming field. And we take the Hodge star of that difference, which would be the tangential components of the magnetic field, they're equal to the tangential components of the incoming field. So the total fields from the inside and outside are continuous across the boundary. Okay, so this is 3 boundary conditions, which is a somewhat unusual number for an electromagnetics problem. But you can actually show that the set of solutions to this problem is parameterized by 3 functions on the boundary, plus actually G complex numbers, where G is the genus of the boundary. Okay, so these conditions, coupled with the PDE, imply that the current is going to be tangential to the boundary, which again, physically what we expect. Okay, so an interesting thing about this problem is that there's topological data. So if the genus G of the boundary is positive, these conditions do not suffice to determine the solution. So, of course, anyone who's actually had an MRI knows this from personal experience. The static magnetic field in the superconducting magnet is not generated by an incoming field. It's just there. It's a permanent magnetic field. So we let AJ and BJ be a basis for the one homology of the boundary, and we divide them into two classes, AJ and BJ. And the way we do this is that the AJs are boundaries of surfaces, SAJ, that sit inside of the region, like that what we call an A cycle. And the B cycles, bound surfaces SBJ, that sit outside of the region. Okay, so the topological data is given as follows. The boundary conditions and the PDE, they imply that D of the Hodge star of the internal magnetic field on the boundary is 0. So the A periods can actually be freely specified. So AJ is data, and it is the requirement is that the tangential, when you integrate basically the tangential components of the magnetic fields, the eta I and eta scattered, over these cycles, you get these numbers AJ. And on kind of the PDE, this is the same as the flux of the current through that surface SAJ, which sits inside of the superconductor. So you're specifying the fluxes of the currents or the circulations of the magnetic fields. Now, it follows from Stokes' theorem that the B periods are actually determined by the incoming field. So you can't specify them. They're already specified. Okay, so there is a layer potential representation for these fields, which is given below. And using this representation, you can prove that for any London length, any lambda L in 0 infinity, this data has a unique solution. An interior magnetic field, an interior current, and a scattered field. The representation can be used to define a numerical method, and it involves solving second-kind Fredholm integral equations and inverting the surface Laplacian. Okay, so I'm not going to make you think about this much more. I just want to show you the picture. This is our what's so-called Debye source representation for the magnetic field, the Debye source representation for the current inside of the region. This is the Debye source representation for the static field in the exterior. To get solutions, we need to have certain relations between these different terms. And they're all represented by layer potentials. And they're layer potentials in terms of this GI over L, lambda L, fundamental solution. So we're not going to use this representation, so we're not going to look at it too much further. We do get a system of equations on the boundary of the region. It's a Fredholm system. The unknowns are these scalars R and Q, and vectors of harmonic one forms. These equations turn out to be perfectly okay, at least theoretically. They're Fredholm of index 0. You can prove a uniqueness theorem that shows that they're always solvable in principle. And in fact, practically speaking, you can solve these equations as long as the London length is bigger than about 10 to the minus 2. Now, the problem is that the equations involve this kernel function, GI over lambda L. We see that in the numerator, you'll have e to the minus distance between x and y divided by lambda L, which means that as lambda L goes to 0, you need to use more and more and more points to resolve the kernel near the diagonal. So that means for macroscopic size objects, it becomes really impractical to use the integral equations, even though theoretically they're perfectly okay. You can't really solve them in practice. Okay, so the rest of the talk is about how to find an accurate approximate solution when the London length is a lot less than 1. But let's first look at a couple examples with moderate London length. Okay, so this gives you an idea what the problem is with the kernel. If the London length is 1, that's just the potential produced by putting the constant 1 on the boundary of the starfish. And you get this nice looking, pretty spread out looking potential. On the other hand, if the London length is just 0.1, which isn't even that small, we see that the potential is very, very concentrated near the boundary. So here are magnetic fields on what we call the stellarator, generated by no incoming field, but we specify the circulation around the A cycle, which is the one that goes around goes through the hole in the torus. And we see the field, that's the magnetic field. It looks like that. And this is for different London lengths. And if you look here at the scales, it goes to 0.26, 0.35, 0.38 as the London length varies from 1 to 1 over 64. Nothing very exciting is happening. But if you look at the current, you see that the scales vary quite a lot. So at 1, the largest value of the current is 0.62. At 1 over 64, the largest value of the current is 13.31. So it's already starting to look a little problematic. Now, here's the cross section. So this is what the current looks like inside of the superconductor. So at 1, the current occupies a big region. At 1/8, it occupies a smaller region. And at 1/64, you can barely see the current. That's the skin depth inside of the superconductor where the current sits. Okay, so the problem is that in the limit, as lambda L goes to 0, the problem is that the current actually converges to a current sheet localized on the boundary. Its limit is only a distribution. It doesn't have a limit that's a function anymore. So to deal with this, we have to reformulate the PDEs without an explicit mention of this current. So we denote the solution. We now put in lambda L, lambda L, lambda L, so we know that we're solving the problem with a specific lambda L. So again, we specify an incoming field, we specify some topological data, we let lambda scattered be, and eta scattered lambda L be the outgoing harmonic 2 form. We let lambda minus eta minus lambda L is the closed 2 form, so it satisfies that equation, and it also satisfies that equation inside of D. If we just set the current equal to the divergence of the magnetic field, we get a solution to the original problem. So, which along with this magnetic field will satisfy the boundary conditions above and the flux constraints. So what we need is a good guess for the limiting solution. So for simplicity, we're going to restrict ourselves to the case that the incoming field is 0. Okay, so in the limit, the magnetic field is going to vanish in D identically, and the current converges to a sheet on the boundary. So we assume that the boundary conditions carry over to this case. What we expect is that the limiting magnetic field in the exterior is going to be an outgoing harmonic 2 form with vanishing restriction to the boundary. That means vanishing normal component and the prescribed periods. So we call that field eta H plus, and it's uniquely determined by these conditions that it's a harmonic 2 form. Its restriction to the boundary is 0, which means the normal component of the field is 0. And it has certain periods over the A cycles. Now, the jump in eta H plus across gamma is going to be equal to the limiting current sheet. Okay, so we make the following guess for our solution when lambda L is small but not 0. So the scattered field should be the limiting field plus star D UL, U lambda L, in the exterior. In the interior, the field should be a harmonic star D of a harmonic function, a specific 1-2 form that we're going to write down on the next page, and some correction term here. And these two functions, U lambda L and V lambda L, are just harmonic functions. Okay, so now this is sort of the key thing, is this 2 form, which is going to give the leading order behavior of the solution as lambda L goes to 0. So it has to be a closed 2 form. We're going to specify that its tangential components are the tangential components of the limiting field. And we're going to specify that we can construct this thing and we can control certain norms. So its norm in the L2 norm on the inside domain is going to be something like the square root of lambda L. So I'm saying it's less than this, but it's actually proportional to this. It's not smaller than that. And if I apply the operator dd star plus 1 over lambda squared to this thing, I get something which is like C over square root lambda L. So again, that's better than you would expect by a factor of 1 over lambda, by a factor of lambda, right? Because I have this 1 over lambda squared here. Okay, so now actually here's a formula. We're going to write it down as e to the r over lambda L, where r is minus the distance to the boundary. That's what we expect. We expect the thing is going to be concentrated in the neighborhood of the boundary of size of roughly lambda L. So dr is the distance to the boundary. Gamma is going to be some one form that I'm going to write down in a sec. And then there's going to be some correction term to make it closed. And the correction term is going to be a function times d of this gamma. So r is the distance, pi is the nearest point map to the boundary. And here's what gamma is. I pull back the tangential components, essentially, of the limiting field from the boundary to the interior. And here is this function I multiply by so that this whole thing, this whole quantity, is going to be a closed two-form. So, and then I cut it off. There's some cutoff function which appears there, and it appears here. Okay, so this is something which is completely computable from the limiting solution. And it's supported in a neighborhood of the boundary which is of order size lambda L. Okay, so it has additional property, which is that if I take beta and I restrict it to the boundary, then it's this function e lambda sub L times a fixed two-form, d gamma. And e lambda sub L is smaller than a constant times lambda sub L, which is very easy to see from this formula. And gamma, again, is independent of lambda L. Okay, so remember that I'm guessing that my magnetic field in the domain D is given by this beta, which I've just constructed, some harmonic function, d star d of some harmonic function, and then some correction term. And the scattered field is the limiting field in the exterior plus star d of some other harmonic function. Now, the conditions that we have to figure out what the boundary conditions are for each of these various terms. So first one is that we want the tangential components of this correction term, this omega lambda L minus 0, to vanish. And that implies that the two harmonic functions should be equal to some function, some unknown function f across the boundary, and their normal derivatives should differ by the restriction of that term to the boundary. Okay, so the function f has to be determined. So the equations satisfied by eta minus and d eta, or d eta minus is 0, and this Laplace equation. And the point I'm making here is that a priori we just have the dd star plus 1 over lambda squared eta minus is 0, but d eta is 0. So actually we can write this as the Laplacian of 1 over lambda squared eta minus, where the Laplacian here is the Laplacian on two forms for which the tangential components are 0 and the tangential components of d eta are 0. That's what the boundary conditions are. It's called the absolute Laplacian. And the important thing to know is that closed two forms are an invariant subspace for this operator. So I'm looking at a closed two form, and so I'm actually in a position where I can use this whole operator, which is convenient, right? Because dd star is not an elliptic operator, but that is, Laplacian A is an elliptic operator. And I'd always rather use an elliptic operator when I'm doing analysis than something like dd star. So that's the first observation, is that I'm free to replace dd star with Laplacian A, which will make it a lot easier to prove estimates. Okay, so we can figure out what the boundary data is, this unknown function f. It's the single layer potential of these two things restricted to the boundary. So this is the field, the correction field in the interior, plus this beta field, which I wrote down a formula for. I restrict them to the boundary. It's a two form on the boundary. I divide out by the volume form, the area form of the boundary. I get a function. I apply the single layer operator to that. That gives me my unknown boundary value. Okay, so now I'm going to define an operator on two forms. So I take the two form, I restrict it to the boundary, I compute its single layer, and then I apply star d to it, which is basically what I do to get these two functions u and v. Then star dv lambda is just given by this operator applied to that data. Okay, so now the reason I'm doing this is I want to rewrite an equation for omega that doesn't require anything for which I know all of the data. So this is what for this correction term, this omega minus zero, well, omega minus zero is that sum of terms. So the equation is that that's equal to zero, which is the same as that equal to zero. And the point is, this is the only thing I don't know. I know all of the rest of these things. This as this equation, which is that operator, Laplacian plus 1 plus b over lambda L squared applied to eta minus 0 lambda L. And that's equal to that same operator applied to beta L. So the point is, I know the right-hand side. So now I'm just trying to solve an elliptic PDE with a known right-hand side. And so now what I've succeeded is finding an equation for just this correction term all by itself. What happened? Okay. Okay, so the result that makes all the analysis work. So here's the problem. The problem is I have Laplacian, and then I add this thing to it. And the problem is I need to know that this thing is still invertible, right? Laplacian plus 1 over lambda L squared, that's surely invertible. But then I'm adding this other I plus b over lambda L squared. I need to know that that's invertible. Okay, so here's the sort of workhorse result, which is that this operator is bounded and self-adjoint, and it satisfies the estimate that b theta theta over theta theta, it's smaller than or equal to 0. So it's actually a negative semi-definite operator. It's bigger than some minus m, which is bigger than minus 1. And so what that tells me is that term there, I plus b, is going to be a positive definite operator. So once again, what I'm adding to the Laplacian is something positive definite. So this is going to be an invertible operator. Okay, so the proof of this is mostly the Calderon identity, which says that the double layer composed with the single layer is equal to the single layer composed with the normal derivative of the single layer. And the fact that the spectrum of the normal derivative of the single layer lies in the interval minus a half, a half. Okay, very classical theorem. It's probably theorem known to Gauss. Okay, so now it follows from the theorem that a lambda L theta theta is bigger than d star theta plus a positive number, from which it follows that a lambda is actually an invertible operator. It's a self-adjoint operator with a positive lower bound. It's obviously invertible. It implies the estimate that the inverse of this operator as a map from L2 to L2 is smaller than c lambda L squared, which is a great result, and many other estimates. Okay, so using these estimates, I can show that this is the correction term in the interior. Its L2 norm is less than a constant times lambda L. Now recall that the leading order term that I wrote down has L2 norm proportional to square root of lambda L. So it shows that, yes, the correction term is indeed lower order than this leading order term that I wrote down. And it shows me in the exterior that the difference between the scattered field and the limiting field is also something order lambda L. So the scattered field does converge to the limiting scattered field. Now, the current is given by the divergence of beta plus lambda L minus 0. The other term was already a divergence. It was already something. So when I apply d star to that thing with the harmonic function, I get 0. So this is all I get. Now, we know that the divergence of the magnetic field is bounded and it tends weakly to 0. If psi is a smooth 2 form, then I can compute this pairing between the current and the 2 form, and I can integrate it by parts onto the boundary, and I see that J lambda L minus does converge to a current sheet on the boundary with strength equal to exactly what I hoped, the tangential components of the magnetic field. Okay, so I get the right limiting current. It gives a pretty good picture of the limiting behavior, but the error estimates are off by a factor of square root lambda L. Right? One expects to get a full power of lambda L as the difference between the leading term and the next term. And the reason that it's off is that this v lambda L is only a harmonic function. So in effect, it satisfies the wrong equation in the domain D, where in the domain D, it should be harmonic plus 1 over lambda L squared. So that's not the function, the equation it satisfies. So we can only really expect good estimates for the sum of the two terms. Okay, so let's see what we can do. Okay, so here's another horrific expression where I'm saying I want this d of lambda L. That's the L2 norm of this thing, which is this error term. I write it out in terms of all of the various operators. It's not worthwhile looking at that. I split that into two parts using the triangle inequality. I get that term and that term. Now, the second term is already lambda to the 3/2. So that term is already of the right order. It's that term that I'm wondering about. Now, if we look at that term carefully, we see that as lambda L goes to 0, what happens is I get B acting on beta minus 1 plus B times 1 plus B inverse acting on B beta, which of course is 0. So it does in fact go to 0 as lambda goes to 0. Now, we're going to make usage of the fact that B beta only depends upon the restriction of beta to the boundary, which is this number, just E lambda times D gamma, which is a fixed 2 form, and that number is order lambda L. So we're going to just let chi be B applied to this D gamma, which is a smooth 2 form, smooth closed 2 form on my domain. And we're going to remove the lambda L dependence just so we don't have to keep track of it. In the end, we know we get to multiply everything by this E lambda L. So we're going to look at this. This quantity here is a little bit hard to think about. This quantity is just a little bit easier to think about, and it'll turn out to have the same behavior. So what we're going to do is we're going to look at this d tilde, which is this E, times the L2 norm of chi minus the inverse of Laplacian of lambda L squared dd star plus I inverse applied to chi in the L2 norm. So we've removed the B operator. Okay, this is just for we simplify and we're going to prove an estimate for this. Of course, to really prove the theorem, we have to go back and prove an estimate for the correct thing. But let's just talk about how to prove the estimate for this. That's complicated enough. So how we're going to do this, we're going to introduce an orthonormal basis for the Laplace operator acting on closed forms. Psi j are the eigenforms, mu j are the eigenvalues. So if chi has the expansion aj psi j, then this number, which I'm trying to estimate, is E squared, which is the number which is order lambda squared, and it's times this sum of terms. So the coefficient squared, the eigenvalue squared, lambda L to the fourth, divided by 1 plus mu j lambda L squared, all squared. Now, the rate at which this quantity goes to 0, as lambda L goes to 0, is determined by the rate of decay of the coefficients aj. And we'll see this on the next slide, the exact way that they're related. Now, if my form chi is a smooth form, but it's not in the domain of the operator, right? If it were in the domain of the operator, then actually what I would know is that I would know that the numerator itself has this finite square sum independent of I could just forget about that. aj squared, mu j squared would be finite in this sum. And I could just factor out a lambda L to the fourth. But that's not true. It doesn't satisfy the boundary condition. So it's not in the domain of the Laplacian. But it is a smooth 2 form. And this is something, I have to say, it's something I wondered for years. If I just have a smooth function and I represent it using a Fourier, let's say a sine series on the interval, I know that the smooth function doesn't satisfy the boundary conditions needed to get good convergence for a sine series. That is, it doesn't vanish at the boundary. But is there some estimate I can prove? Okay, well, the following general fact is true. If you take a smooth closed form in a domain, it belongs to the domain of the operator to the t power as long as t is less than a quarter. And the reason is very simple. It follows using an interpolation estimate and the fact that the Sobolev space of order S is equal to the Sobolev space of order S sub 0 if S is between minus a half and plus a half. Right? That is to say, once S gets to be small enough, it can't tell what the boundary behavior of the function is, of the distribution is anymore. And you take advantage of this and conclude that you get this fact that smooth forms belong to the domain of the operator to the t power for t less than a quarter. Well, that gives us the following estimate. It implies that that sum, mu j to the 2t, aj squared, is finite for any t less than a quarter. If you use that estimate, you can estimate this d tilde of lambda L squared as being lambda L to the 4t times this sum here, and the sum is smaller than lambda L to the 2 plus 4t times this finite sum, as long as t is less than a quarter. Okay, so it proves, and in fact suitably modified, this argument proves that this quantity d of L is less than lambda L to the 1 plus alpha for any alpha less than a half. So I've almost gotten back my full order of lambda sub L in the error estimate, where again we recall that the norm of beta L is around square root lambda L. So I've pretty much picked up a full order. Similarly, we can show that the norm of the current plus the leading minus the leading order term of the limiting thing is also in the L2 norm, smaller than lambda L to the alpha for an alpha less than a half, which is a very nice thing since these are both converging to distributions. The error is still small in the L2 norm. Okay. Now, am I running out of time?
More 10 minutes? 10 minutes more or
10
less.
minutes more?
Yes,
Okay.
it's okay.
Okay. Okay, so that was sort of an interesting sort of warm-up case, and we're not going to go through the details of the general case, but it was an interesting warm-up case. But the fact is that the current flows in a small neighborhood of the boundary of a superconducting region. So really, when people build superconducting magnets, they don't use a chunk of material. They use a thin sheet of material. And what we're going to do here is we're going to replace this bulk thing with a tubular neighborhood of a smooth embedded surface, let's say of genus G. So its complement now consists of an unbounded exterior region, omega plus, a bounded interior region, omega minus. In the bounded region, we again have the London equations. Now I'm going to call the interior solutions, I'm going to use a superscript 0 to indicate the interior solutions. They satisfy the same London equations. In omega plus and minus, in the exterior regions, we again have the equations of magnetostatics. In each region of omega plus or minus, there's an incoming field as well as topological data. So in the exterior regions, the total field is going to be the incoming field plus a correction field. The correction field is going to be outgoing, and we're going to have boundary conditions. The magnetic fields are again continuous across the boundaries, just like before. So these are the normal components are continuous, the tangent components are continuous. Now, the specification of the topological data is quite interesting when you have two surfaces like this. On the outer boundary, periods over the A cycles, so the ones that bound surfaces inside of the domain, are again data. They're against, you have to specify these to get a unique solution. Now, in the inside, the B cycles will bound surfaces, and you have to specify periods over the B cycles for the inner boundary. So you have an inner boundary and an outer boundary, and one you go around this way. The outer boundary you go around that way, and the inner boundary you go around that way. So the topological constraints are these, that the tangent, we integrate the tangent part of the magnetic field around the A cycles and to get these, the exterior A cycles to get specific constants. And we integrate the tangent component of the magnetic field around the B cycles for the interior component. Now, the curl equation implies again that the divergence of the field, the magnetic field inside the region is going to be the current. And it implies that the fluxes of the current through these spanning surfaces. So the spanning surfaces are these purple surfaces. The A cycles span something that looks like that, and the B cycles span something that looks like that. So the current, the A current flows this way, and the B current flows that way. And it says that the differences of these numbers will be the A current, it will be the current through the A spanning cycle, and the differences of those, the B's, will be the current through the B spanning cycles. Okay. So as before, we assume the solution can be written as the limiting harmonic fields plus star d of harmonic functions in the exterior regions. And in the interior regions, it's this beta lambda L, which really is the same thing as before. We just construct a beta lambda L in the boundary in the neighborhood of either the interior and exterior boundaries, plus again, star d of a harmonic function and a correction term. V lambda L is harmonic, beta lambda L is explicit, and this is a solution to the same equation as before. Now, we have this operator which I call curly B. Curly B is the same idea as B. That is, I take a two form in the interior region, I restrict it to the boundary, I divide out by the area form, I extend it using the single layers from both boundary components into the interior, and then I take star D of that to get another two form. So it's an operator analogous to B, but accounting for the fact that boundary omega has two components. So now, as before, we can show that on an appropriate domain, the operator on the left-hand side here, that operator, is invertible in closed two forms, and it gives a proof of the existence of a solution to the boundary value problem posed above. Now, working a lot harder than before, we can show that the correction term to the magnetic field in the interior is big O of lambda L to the 3/2 minus epsilon. And the difference between the magnetic fields and the limiting fields in the exterior is big O of lambda to the 1 minus epsilon. The current minus d star of beta L. So beta L is this explicit form. D star beta L is the limiting current. The difference is, again, in the L2 norm bounded by lambda L to the 1/2 minus epsilon. Point-wise, both J and B and beta are of the form OE to the minus R over lambda L. So both of them are concentrating very strongly at the boundary of the region. Okay, so here numerically, we did an experiment, and this shows the rate of convergence of the field in the interior to the limiting field for a thin shell torus, and that with zero incoming field, and we specify that the circulation around the outside circle should be 1, and the circulation around the inside circle is 0. And we see here that this is the L2 error, this is lambda L. Everything is on a log, both it's a log-log plot, and we see that it looks pretty strongly like it's converging order lambda L. Of course, we couldn't get you can't get to very small lambda L's in order to make comparisons between the actual solution and the approximate solution. Okay, here are some pictures where we have these are the magnetic fields. Lambda L is 1, lambda L is an eighth, lambda L is a 64th, and lambda L is 0. So that you can see that between the 64th and 0, the picture doesn't change very much. Again, with no incoming field, and A1 plus is 1 and B1 minus is 0. Now here we also have the current, and here's lambda L is 1, lambda L is an eighth, lambda L is a 64th, and the thing to note is that the scales are totally different. So at 1, the maximum value of the current is 0.91. At an eighth, the maximum value of the current is 0.389. And at a 64th, the maximum value of the current is 30.57. So the current is getting much, much larger and much more concentrated near the boundary. Okay, so I guess I'll wrap up here that the Debye representation, it gives a good method to solve the London equations, provided that the London length is not too small relative to the size of the region. The representation becomes ill-practical and ill-conditioned as the London length goes to 0. So using this direct analysis, where we actually just rewrite the whole problem in terms of a PDE for the magnetic field alone, we can obtain a very accurate approximate solution, even for lambda L about 10 to the minus 7, which is of physical interest. Okay, so here's a question. So suppose you take a form, which is a smooth form in a domain, a bounded domain, smooth 2 form. The smooth 2 form is not in the domain of the Laplacian to the 1/4 power. But is it still true that this sum is actually bounded by a constant times lambda L to the 1/2? Now, this is true in one dimension for an interval. It's true in two dimensions for a circle. It's true in three dimensions for a ball. So what's very interesting is that it really relies upon the smoothness of the forms tangent to the boundary that you end up getting this estimate, even though the form is not in the domain of the quarter power, the Laplace operator to the quarter power. So I wonder, and I think it's probably true, that this estimate always holds, even though the reason is not quite that it's in the domain of the quarter power. It's in the domain of the Laplacian to any power less than a quarter, which gives you lambda to any power less than a half. But I think lambda to the half is probably actually correct. So now the other question, I mean, the natural question is, can you actually compute an expansion in lambda L for these solutions? So I computed the first term and I showed that it's almost a leading term in the sense that the error is almost order lambda L. So the question is, can you compute the next term? Can you prove that the difference between the first term and the next term is order lambda L? So it's a very good question, and I don't really know the answer. Okay, so well, thank you very much. I'm really sorry I came late.
It's okay, Professor. Thank you very much for this nice talk. Let me open for some questions or comments. Please, the audience is open, the microphone. You can ask Professor Charlie some questions or comments. I just have curiosity. I work in evolution equation, and you told in the beginning the problem involved time dependence is too complicated.
Uh-huh.
There are some results using the time dependence or not?
No. I mean, the
No.
problem is
Okay.
the time to if you as soon as you have even a harmonic field,
Mm-hmm.
the nature of the material is different. So
Mm-hmm.
the problem is that this idea that a superconductor is a macroscopic material is only true in the static regime. As soon
Okay.
as the current is time dependent, what happens is the material itself kind of breaks up into superconducting and normally conducting regions.
Mm-hmm.
But in a way that it's like a composite material, it doesn't really have macroscopic regions that are either superconducting or normally conducting. It's incredibly complicated to really describe it. I've never really been able to understand what it is physically. So
Okay.
that's why I haven't tried to do that. I just, the model that people use is the Ginsburg-Landau equation
Mm-hmm.
to sort
Yes.
of describe how the material's conductivity properties depend spatially. And it's
Mm-hmm.
a nonlinear PDE, and it's for this function phi, which takes values between 0 and 1, right? Where it's 1, it's superconducting. Where it's 0, it's
Mm-hmm.
normally conducting. In between, it's hard to say exactly what it is. So
Okay.
it's a very, very,
Okay.
it's just a vastly more complicated question as soon as you have anything time dependent.
Okay. Okay. Nice.
And type 2 superconductors, you can't even start talking about them without talking about Ginsburg-Landau.
This
So,
was normal. Yeah.
and
Yeah.
actually the kinds of superconductors that are actually used in any real application are always type 2 superconductors because
Okay.
they're the ones that have sort of they're high temperature superconductors,
Mm-hmm.
right? Which means
Okay.
like 20 degrees Kelvin instead of 2
Yeah.
degrees Kelvin.
Yeah. Yes. Nice. Okay. More questions or comments for Professor Charlie? The audio is open, the video questions, no? If not, let's say thank you again, Professor, for this nice, very nice talk. Thank you very
Okay.
much.
Thank
Thank
you.
you. Thank you for inviting me.
Thank
Thank
you.
you.
Bye.
Bye bye.